So I'm going to be reviewing sort of like the way that I like to approach solving interview problems. I think it really helps to have sort of a methodical framework um, to solving the problem. Um, and yeah, like so in weightlifting, sorry, I keep using weightlifting analogy just because that's like the hobby that I personally enjoy. But you know, in jiu-jitsu too, um, you really want to just sort of drill certain movements and just really hammer certain pieces together. So it's the same if you like played an instrument. It's like you want to, you know, have a systematic way to learn a new song, or you want a systematic way to learn a new lift by breaking it down into components and then, you know, building out different components. So if you bench press, you might do board presses. You might have a phase where you just work on board presses. Um, but yeah, so I think it's beneficial really to have like a really super methodical framework to doing all of this. So like the framework that I like is just one, just try and understand the problem, just like read it, just make sure that you kind of like understand what's going on. And as part of that, like you want to try some test cases from very simple to hard, and then you want to describe an approach in pseudocode. And I see a lot of people struggle here because they either skip this step entirely, or they either like skip this step entirely, or they like are imprecise in the way that they're writing their pseudocode. And then number four is actually pretty easy. You just translate to code, you run it, you debug it, and then you know I personally really like Python for doing these interviews. I've actually done these interviews in like C++, um, and it's really hard. Um, I think the higher level of the language, the easier it is to do. I've actually had like a little bit of success using Haskell, just because it's like really, really high level, and it makes things really like if you are confident in Haskell, yeah, like basically the higher level of the language, the easier it is to do because the less code you have to write. All right, so let's just dive into this problem. So this I would say this is like a medium level recursion problem. You might get asked this in a phone screen, but it's not that hard. So let's just understand the problem. So a frog can jump upstairs one step, two steps, or three steps at a time. So we need to write a function to count the number of ways for the frog to jump up n steps. And you know, we'll say n is greater than or equal to 0. Okay. So let's say that our function is f. So like let's just go through some test cases, right? So I think I understand what this means. So like a frog can jump up 0 steps in only one way, right? Um, and then a frog can jump up one step in one way, right? And then a frog can jump up two steps in, well, he can do it like one step at a time, right? And then he can also do it jumping up two steps at a time. So you can think of it as like 1, 1, and then he jumps up 2. So he he did 2 jumps versus he did 1 jump. So that's 2. And then f of 3 is equal to him jumping up like he can jump up 1 step 3 times, or he can jump up 2 steps then 1 step, or he can do 1 step and then 2 steps, and then he can jump up 3 steps. So I think that's like that's 3. So let's just say that like we can think of it as like he just does 1, 1, and then 2, and we'll use like a list. Okay, or he does like 1, 1, 1, and then he does 1, 2, and then he does 2, 1, and then he does 3. All right. So I'm like, huh, okay, this is that's pretty interesting. Okay, so this seems like there's like a recursive relationship just off of pattern matching, but let's actually go through it super slow. Like I'm just gonna like I'm gonna say like let's say you don't know recursion, or you're not that familiar with recursion. You can't just pattern match it for a recursive relationship. So you're just like, okay, how do I do this? One way is actually you just keep grinding through examples. So let's go through this. You can go 1, 1, 1, 1. He can go 1, 2. He can go 1, 3. He could go he could go 3, 1. He could go 1, 2, 1. He could go 1, go 2, 1, 1. And he could go, hold on, let me break this up. Somewhere somebody out there is like, this is really, really slow. Okay, 1, 2, 3, 4, 5, 6. Okay. So like immediately I'm kind of like, huh, that's 6. All right, so like 6 is equal to 1 plus 2 plus 3. That's kind of interesting. I wonder why that might be. And we happened to write this out, like we were pretty methodical, so we're like, huh, there's kind of this interesting pattern here. I'm not going to do 5 because I think 6 is enough, or 4 cases, or I guess 1. Yeah, 5 cases is enough. So let's take a look at this. Okay, so, and it's kind of interesting too because 3 is 0 plus 1 plus 2. Okay, so it seems like I kind of have this hypothesis. All right, I got this hypothesis. Call me crazy, okay? That maybe f of n equal f of n minus 1 plus f of n minus 2 plus f of n minus 3. All right? And, I could go out and like do all the computations, but let's just like, I have two, I can look at 2 cases like f of 3 and f of 4 to try and figure out if there's some way to like justify my hypothesis. All right. So like 15 is just is like do nothing, right? Like the frog the frog is just chilling. He's on a lily pad. He's just chilling. And then 16 is actually like it seems like the frog just does that, yeah. 2 is kind of interesting. Like we added the case where he jumps up by 2, and then we took the case where he jumped up by 1, and then we added 1 more. Like, so like I can kind of see that like, oh, the frog can jump up 1 step. If the another way of thinking about it. Okay, sorry, I got a little bit tripped up, but like, what if we simplify the problem? There's another great way to solve things, and we say the frog can only jump 1 step. Well, I think that's pretty obvious that f of n is equal to 1. Okay, the frog can like literally only jump 1 step at a time. Okay, so what happens if he can step? If he jumps 2 steps? If he can jump 2 steps? Well, f of 0. Well, this is kind of interesting because he can jump, like it seems like I have a similar hypothesis here, right? Which is that f of n equal f of n minus 1 plus f of n minus 2. So how might I be able to justify this? Well, let's say like the frog has n minus 1 ways to, or he has this number of ways to jump a step behind him. Okay, so let's say n is 10. Okay, there are f of 9 ways to jump to the 9th step. If we're at the 9th step, the frog can only jump to the 10th step in 1 way, right? So if we're at the 9th step, the frog can only jump to the 10th step in one way. So if we're at the 8th step, the frog can only jump to the 10th, can also jump to the 9th step, but that's already included in the previous case. So there's only one way, one new way to jump to the 10th step. Yeah, so another way you can think about it is, let's say we work backwards. So if we work backwards, then like if we start at step 10 and we work backwards, then the only other step, we can end up at step 7, 8, 9 by jumping 1 step, 2 steps, or 3 steps, okay? And then we can just count the ways to jump to 9, 8, and 7 and just add them up. If we allow, the frog to jump 1, 2, or 3 steps. So you might be wondering, well, how come, how do we know that they're actually distinct? Well, they're distinct because the last jump is either 1, 2, or 3. So when we, take this sum, we're all the paths are distinct because the last jump of each set of paths is different. So the last jump for the case derived from this subproblem is always going to be 1, and the last jump to this subproblem is always going to be 2. So those pieces are completely distinct. So we're not double counting anything. Yeah, cool. So all right, so we tried some test cases, and actually we had this hypothesis, and this actually translates pretty well into pseudocode. Like this is basically pseudocode. Like literally, the pseudocode would just be something like this: f of n equal n, f of n minus 1 plus f of n minus 2 plus f of n minus 3, and then f of 0 would be f of n equal 0 for n less than 0, because there's no way for a frog to jump negative steps. I mean, technically a frog could jump negative steps, but could jump backwards, but in this case, this is a very forward-looking frog. He never retreats. He's an aggressive frog. He's going places. He's going n steps places. And then f of n equal 1 for n less than that's basically it, man. Like f of 0 is equal to 1. And then you'll actually see that this will work out. So f of 1 is equal to, so for example, f of 1 is equal to, using our recurrence relationship beneath us, is f of 0 plus f of negative 1 plus f of negative 2, which is equal to 1. Okay, and then f of 2 is equal to f of 0 plus f of negative 1 plus, f of 1 plus f of 0 plus f of negative 1, which is equal to 2. And then f of 3 is equal to the sum of these previous ones, and that is that right? Hold on. Did I do this wrong, man? Oh yeah, shoot. Okay, so sometimes I make mistakes. That's my bad. Did I miscount something here? 1, 1, 1, 1, 1, 2, 4, 2, 1, 2, 3. Huh. Oh, you know what? I missed this case. All right, so yeah, be careful when you are enumerating cases. Maybe you should just jump to the recursion, because I clearly cannot enumerate cases properly. All right, anyways, f of 1 equals 4. All right, so the recurrence relationship holds for all n greater than 0. So literally, our code will just be f of def f of n if n less than 0, return 0. If n equals 0, return 1. Else, and then otherwise we just return f of n minus 1 plus f of n minus 2 plus f of n minus 3. Okay? At this point, your interviewer will probably ask you, hey, like, what's the big O of this in terms of performance? What's the runtime of this? And you'll notice that each time we make a recursive call, we are creating a tree, or where we are calling 3 separate functions. So, for example, like f of n equal f of n minus 1 plus f of n minus 2 plus f of n minus 3. Okay, and then every time we call f of n minus 1, we are again calling 3 separate functions, and we do that 3 separate functions, and we do that, kind of across all 3 functions. So, it seems like we would call the big O is going to be 3 to the n. Okay, so you're like, that's not so good, that's not awesome. Okay, and so what I would do from here is I would memoize, and this is basically top-down dynamic programming. For those of you who want fancy terminology. And all memoization is it says it's basically a hash map or a dictionary, and it just says, hey, let's store the value before, like every time we find a result, let's store the value. Okay. Memo. All right. And so now this is actually O of n with O of n runtime and O of n space. Let's break this out. So why is it O of n runtime? Well, let's talk about the space. So when we call f of n, we are kind of basically doing like a depth first search in terms of like the tree. So the tree might look something like f of n, and then f of n minus 1 plus f of n minus 2, okay, plus f of n minus 3. All right, but then what the next call that we call into our function call stack is f of n minus 2 plus dot 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 and so forth and so on. And so as we go through our tree, we after we've done all the way down to f of 0, we've cached all those results, or we've solved f of 0. We go up, we solved f of 1, and then it'll probably look something like this, or it'll look something like this. It'll be like f of 0 plus f of minus 1, and all of these results can be computed in constant runtime. In fact, f of 0 will already be cached because we've already encountered it here. And then f of 2 will be called f of 1 plus f of 0. And again, we've already encountered f of 1 and f of 0, and f of 2 got computed just now. So the because we are calling, because the recursion goes through the call tree in depth first search, you can see that we have like really on call stack blocks. We only really have on blocks in our call stack, and then the memo space, the space for the memo dictionary is only on as well, and that lives in global memory. So we are basically recursing through this, and then as when we would normally do a new recursive call, we actually skip that because we've memoized it, and it's just a key value lookup in a dictionary, which is O1. And so that's how you know it's on space, and then that's also how you know it's on runtime, because each of these, each layer is actually just a sum of memoized layers that were called beneath it that run in O1 time. So yeah, you have on runtime and on space using top-down memoization in this manner. Yeah. Another common mistake that I actually see some people make is they'll see the dynamic programming bottoms-up way. For those of you who don't know what that looks like, it looks like this: dpi, j, dpi equal, dp, I minus 1 plus dp I minus 2 plus dp I minus 3. And they'll just start coding it up, or they'll skip talking through the pseudocode. That's actually, you can do it this way, but I actually think it's much better to talk fully through the pseudocode, because it gives an opportunity for you to check in with your interviewer. And so your interviewer can point out things like, hey, your algorithm, I think it's incorrect. Like, have you considered this case? Or, hey, your algorithm looks correct, but your runtime is bad. Or, hey, can you solve this using a slightly different approach? And it's really just an opportunity for you to leverage your interviewer to help steer you towards the right solution. Because, in my personal experience as an interviewer, I really want people to succeed, or I really want to guide people on the test that I want them to take. Because if they go, off-roading, then I can't even evaluate them, because it's like, wait, I'm trying to evaluate you on this track. Like, I'm trying to evaluate how well you can, code on this track that we've defined, so that I can give like a standardized score or whatever to the hiring committee. Whereas instead, like if you go off-roading and you go off the beaten or the track that I'm kind of expecting, I'm just like, I can't help you, and also I can't really easily evaluate you. So I'm just going to try to move you back onto the track. Okay, so that was a lot, and I made some mistakes along the way. So I would say, like, 1, understand the problem. 2, try some test cases from simple to hard. 3, describe your approach in pseudocode. And as you can see, your pseudocode can be fairly mathematically rigorous. So for example, our pseudocode here was this. And this is like, this covers all n from n less than 0 to n greater than 0. And it covers all the subcases. Yeah, so that's kind of it. And also sometimes, I didn't do this because I'm just doing a YouTube video, and but you should also debug as you code if you can. So for example, like maybe I could have I probably could have tested my code as I went along. So I could have tested, print f of minus 1, and then print f of 0, and then print f of 1, if that makes sense. Okay, that is it for me. Let me know if you found this helpful, or if you have any questions, or if you want me to do another video in the comments below. Cool beans.